Hi, I'm Jessica Forde, and I'm here to talk to you about wireless router data. So I'm sure you all can remember the experience of finals season. You walk into the library and you go to the place you typically study at and you see someone has already taken your spot. So you think, okay, well, maybe I'll just try somewhere else, and that place is full, and that place is full, and you end up spending, your whole day when you're supposed to be studying actually just looking for a place to sit. So we ended up being able to say, okay, you know what, let's try to find out how full these study spaces are based on wireless router data and create a tool about it. So myself and a bunch of students at Columbia have created the website Density, and let me share this with you now. Let's see, let me get the, there we are. So this is Density, and Density lists a number of study spaces across campus, and we're actually able to see how full these study spaces actually are. We also have some dining halls and the student center. And so this data is actually updated every 15 minutes, so it's a live feed that helps people to get around campus. We also have a map functionality. And this actually shows us where on campus places are full. So for example, this part of campus is the main library. This actually shows how full various floors on Butler Library are. So as I mentioned, let's get back to this. It's loading again. So as I mentioned, the data is collected from client counts that are available from 6 libraries, 1 student center, and a dining hall. And this is our anonymized counts that are aggregated every 15 minutes. We also provide an API to the Columbia community that allows people to access this data and have the same ability to create tools and understand student behavior or campus behavior in general. So actually, as part of PyData, we are sharing this data with the PyData community. So this is the key you all can use. If you are a member of Columbia, you can just use your Columbia email to get access to the API. And so I'm just going to show a couple examples of the kinds of things that we are sharing with the Columbia community. As I said, data is supplied in a 15-minute window. So if you get the latest route, you can get the latest information for all buildings. If you want to get a particular router, we have a group route that allows you to find out how many people, for example, are on the Butler Library 4th floor. We also can aggregate this data up to the building level, so you can look across multiple floors and look at each floor for the latest timestamp. So for example, if you looked at Butler Library, we can just click on this here, and the JSON with the latest data will come up. So here it is. So this is what it looks like, as I mentioned. So you have our client count, which is the number of devices connected to the router, the time, the ID of the location, the ID of the building, and our estimation for how full the space is. We also have the ability to share data within a time window. This is also available for both groups and buildings. And you can also just aggregate based on this particular day, both by building and by floor. So for example, for this example, we're looking at John Jay, which it has a bunch of dining halls on October 10th from 8 a.m. to 9:30 p.m. And again, as I mentioned, so these are now you have multiple floors in this building. So we have John Jay Dining Hall and JJ's Place. And we have the counts of the routers, of the number of devices connected to each router over time. We paginate our results. So if you're actually using this to gather more extensive data, we provide a next page link so that you can just keep traversing the results. So if we were trying to actually use this in Python and do some analysis on this, obviously time of day is very important to this data. So I'm just going to share some basic functionality of Pandas that allows us to work with this data. So this is a basic query for the again, the dining hall building John Jay. And this is what it looks like when we pull it in to Pandas. And then we are able to then use the datetime functionality from Pandas to be able to create a datetime index and set that index to our data frame. For any of you who haven't used this yet, the datetime index allows us to do some really basic filtering based on year, date, month, hour. And so for this, I've just done a simple filter on the results from 9 a.m. And so this is what it looks like. And then we actually can also pull out different aspects of the date times based on this index. So we can get the minute, we can get what day of the week it is, we can get the hour. And also, if we're not using, if we're actually just making this a series, right, and we're just putting this in the data, you can actually access this functionality with the .dt. I don't know, if you add .dt to the string, you can actually access all the same functionality in date times for Pandas. So I'm going to share with you some initial findings we found on the data. And we have a Jupyter notebook that has everything, including the actual string for the key, if you guys are all interested in playing with the data. So I'm going to share that with you now. So again, so this is one of our libraries at Columbia. And I'm just going to, I've already loaded some libraries. And as I mentioned, this is the authorization token that I'm sharing with you all. And this is the example, this is an example of the John Jay data that I shared with you earlier. For the sake of brevity, I'm not going to query the whole data set. I'm just going to take something we already have pre-processed. And I've already loaded it and turned this into a date time. So let's see what this looks like. Oh, wait, I have to reload this again. So while this is loading, I'm actually just going to go to our original results. Let's see, so. UCC. Let's see. Density PyData. This data set is pretty large, so I'm going to do that. Okay, so as I mentioned, so this is the Jupyter notebook, as I mentioned, and this is the data we shared earlier. And this is actually what it looks like on the server. So we have our timestamp, we have the ID, we have the name, we have the building ID, the name of the building, and the number of devices connected. So this data set we're playing with is a little over 600,000 entries. This is the full list of buildings that we have available. So as I mentioned, we share definitions of capacity. And so how do we actually do this? So as you can imagine, college students can actually crowd into spaces pretty easily. But we don't want to actually use that representation of something like this where people are having a party in the library during finals to represent how full a space is, because that's actually not representative of typical usage. What we want is to be able to say, a place like this where people are sitting and there's not that many spaces available for you to sit down and study is actually full. So in order to do that, we consider what an average day looks like. So in this example, I'm actually going to create a variable called hrfrac, which is basically just a time of day that's created in decimal points, because we have, as again, the minutes are on 50-minute intervals, so it's a lot easier to work with if we do fractions of an hour. And then I'm going to just create a plot that looks at this time over day. So if we look over here, this is basically what the population growth of devices looks at across Columbia, across all our locations. So as you see, there's like a few people hanging out at Columbia in the libraries early in the morning. Most of the morning, no one's around. And then it really begins to pick up in the afternoon and then slowly decreases into the evening. Interestingly, this is a little different from what you would see in an office building where people come in the morning, take a break for lunch, and then come back. And this is similar to Seaborn's time series plots. We actually have some confidence intervals in here. So you can see there's a lot of variance going on. So as I mentioned, capacity is the level at which population growth stabilizes on a given day. So if we want to look at that, then we would say, okay, you know what is the value under which this population curve growth stabilizes? So it would be somewhere around here at around 3 o'clock, say, right? So then in this case, we'll say, okay, we are full at Columbia then at around 3 o'clock, and so whatever this argmax value is our capacity. So in that case, you know, in this plot, we would say at Columbia, all our spaces are full when there are about 2,443 devices connected at Columbia. Now, as I mentioned, we have libraries, we have study space, we have student centers, we have various study spaces. We also have dining halls. So different spaces actually have different properties in terms of people entering the building. And since everybody now has their phones, you can actually look at who's in the building when and why. Right? So for example, this is a library. This is Butler Library. Butler Library actually behaves very differently from John Jay. So Butler Library, as I mentioned, you have people studying late at night. Nobody's really around in the morning. People come in after lunch, take a break for dinner, and then they go studying into the night. Interestingly, as I mentioned, if you look at router data from office buildings, this will actually be transposed 3 hours earlier. So everybody starts to coming in around 9 a.m., they take a break for lunch, and then they work late into the night. This, instead, is actually John Jay. So this is, I mentioned, our dining hall. So you see there's actually some huge spikes happening at around lunchtime and dinner time, right? And that totally makes sense. As I mentioned, it's a dining hall. So how does campus population change over time? So if we actually look at this population across campus at Columbia for the whole year, we can actually see when people are off from school and when are people not studying. So if you see here, we actually have some really nice cyclicality. If you look in the summer, people aren't typically on campus, and then people slowly start entering to campus. Then we have a big dip around Thanksgiving, and then a big dip around winter break. Then you see the same pattern again happen over winter break, and then people are coming back in for the spring semester. But again, you see there's also, within this time range, some variation as well, which indicates that people aren't necessarily studying equally every day of the week. So in order to better see this, we're going to try to group this weekly data into weeks. So we index by week of year, and we are actually doing a group by the week of year, and then plotting this accordingly. So given the fact that we aren't starting, we have actually data across years. We're doing some manipulation around that to get the indexes to match. If we look over here, this is the same plot now with the data aggregated by week instead of by day. So again, you see this is Thanksgiving, right? That's your drop for Thanksgiving. This is your drop for winter break. This is your drop for spring break, right? And then this is what happens in summer. So again, there's some really interesting cyclical properties in here. So the reason why we had to do this, of course, is because the day of the week affects study habits. So let's try to look at this directly. This is one of my favorite ones. People don't study on weekends. So everybody is around on campus on Monday, Tuesday, Wednesday, Thursday, and then when Friday comes around, nobody wants to be in the library. We can also find some really interesting characteristics of days with unusually high number of devices. So if we go through the days and we say, okay, let's look for days that have unusually high number of devices that day, and we're going to pick some days. So for example, we're going to pick the auditorium, since that's one of our spaces. And the day with actually the highest amount of device counts found is in late summer in 2014. So let's look at what this looks like. You see here, people are coming in for specific periods of the day. This is actually, again, this is late summer, so this is around the time of orientation, which makes sense because you're bringing in the new students and you're actually giving them lectures and things like that. And then, really interestingly, Columbia has a tradition called Orgo Night, where, as I said, people crowd into the library and the band plays. And you actually can find it very easily in Butler Library 2, which is here, which is where everybody shows up at the same time. And as I said, even compared to finals period, there's many more people in the library. So as I said, we've created some tools. This is another example of something else another student at Columbia made. And so we have this data. And we would like to share this with the Columbia community. We would be happy to share this with you all. I'm really curious to see what you all end up using it for. Things that we would like to do in the future. As I said, we've been able to create these sorts of plots. We would love to be able to create some dashboard functionality, be able to allow people to be able to better interact with the data and see trends over time. I'm a machine learning person, so something I'm particularly excited about is prediction and anomaly detection of this data set, since you have some really nice cyclical properties across the week, across the day, across the month. And so this is an example of the cover of Bayesian data analysis, the 3rd edition, which is actually daily data of births from Andrew Gelman, who's at Columbia, and a bunch of other Bayesian statisticians. And if you look here, you can actually see, if you look very carefully, particular anomalous days of the years that have unusually low births. So for example, New Year's Day has really low births, Independence Day, Christmas, Thanksgiving, Labor Day. So we would really like to be able to do something like that. If you want to look at our website, everything's open source. This is the link to the repo. And thank you. Oh, yeah, sure. Questions? Yeah.
So you mentioned anomaly detection. How are you thinking going for doing the anomaly detection for taxes? Are you going to use Zstra or Dusty?
What I'm hoping to do is, so I mentioned this paper is a paper by Aki Vatahi and Andrew Gelman. And so what they basically are doing is they're training multiple Gaussian processes with different kernels. And the kernels are relative to the length of the window of different periods. So you have one that represents the variation that happens on a weekly basis, and then you have one that represents the variation that happens on a daily basis. And from there, you can have a kernel that also represents monthly variation. I mean, if you look, you see here they have they have fit Gaussian processes to tailor themselves to each kind of cycle that's across the month, the year, the day of the week. And so we can actually do a similar thing by looking at actually time of day, because there is some really nice cyclical properties that are very predictable. So that's generally the hope.
But how does that perform compared to the Zstra for the anomaly detection? Because Zstra is a lot easier to
I'd have to think about that. I'm not quite sure.
Because right now, like a lot of people, when they compare anomaly, they just check Zstra, how many standard deviation, standard deviation.
Yeah. I think what we'd like to do is be able to control for some of the variation that happens within that time period itself, right? Because yeah, you could conceivably do that. Of course, you also, doing something like this, you would be able to conceivably borrow across the fact that that you have people in the same building, so you can also be able to hopefully look at in that way as well. I mean, conceivably, doing something within the same window would be a lot more efficient. But I think that, you'd have to think about that. I'm hoping, the hope would be to be able to look for particular events in time, like for example, orientation or something like that.
So have you considered
Yeah, no, we haven't necessarily looked at that. This is, I said, this is very new data, so we haven't really done much analysis on it. Yes?
I'm sorry if I missed it, but I'm curious, so how did you get the raw data? Is it from the router?
So this is router data, yes. This has been provided by Columbia's IT department. So this has been shared with us, and we're sharing this with the Columbia community.
Yes, I'm curious, so what's the style of the raw data you got like that? How strong the signal is?
No, this is the number of devices connected to a router.
I'm also curious, so you have already divided the library to different parts, so do you have the like specific location of each devices?
No, so in order to create the level of anonymization necessary to make everyone happy, we needed to aggregate it on a pretty large scale. So this is even aggregated on the floor level. So even, obviously there are more than one router in a big floor, but we've just taken it all and put it in one bucket. Yes.
Wondering how many, do you have an idea of the number of students that are coming in but not connecting to anyone?
I think that would be pretty hard to tell. I mean, you can use an estimate and you could naively, another thing that we were considering was naively just assuming that one person is about 3 devices or something like that, or 2 or 3 devices, because you probably have your laptop and you probably have your phone and maybe you'll have a tablet. So it's about 2 or 3 devices, and so you can get pretty close at guessing, but without actually going in and doing a census of how many people are in a space, it's really hard to tell. Okay, thank you.